Hello, everybody. Today we'll talk about finite present simple groups and measure equivalence. So this will be separated in two parts. In the first one, I will define buildings and Kac-Moody groups. In the second one, I will give a formula for L2 numbers or groups acting on buildings and exhibit an infinite family of such groups, of finely present simple groups that are pairwise non-measure equivalent. So let me begin the first part. So we are interested in infinite finely present simple groups. So what examples do we know about these groups? The first thing we know that the first thing we see is that we know really few examples of such groups. We know Thompson's group, that is historically the first example, and then later variants due to Grigorchuk, Rover and Krashevich. We have virgin multis groups acting on products of trees. And we have Kac-Moody groups over finite fields acting on twin buildings. So these are the only three examples of infinite finite present simple groups we know to the date. Naturally, we do not study these groups up to isomorphism, but up to other equivalence relations, like quasi-isometry or measure equivalence. So I will focus on measure equivalence. But before, let's say, what do we know about quasi-isometry of these groups? So if we pick virtual multis groups, they all act properly and co-compactly on products of trees. So in them, they are all quasi-isometric. For Kac-Moody groups over finite fields, it was shown by Kac-Moody and Ramy that you can find an infinite family of such groups that are pairwise non-quasi-isometric. And then later it was shown by Skipper, Witzel, and Zaremski that you can do the same thing for Robert and Krashevich variants of the Thompson's group. Okay, just a little remark. This is like the results due to Kac-Moody and Ramy, and then later to Skipper, Witzel, and Zaremski are interesting because it's hard to produce finely presented simple groups. If you do not require finite generation or finite presentation, it is much easier to do this. You can produce easily infinite countable simple groups. So the typical example is you take PSLN of Q. So in general, PSLN of K is always simple for any field K. And if you take PSLN Q, we have a countable simple group. But why it is harder to produce finely generated or finely presented simple groups? I would say the reason is Malkiev's lemma. So Malkiev's lemma says the following. It says that if you have a finely generated linear group, then you are residually finite. Residually finite means that you have normal subgroups of finite index. So in particular, if your group is also infinite, that means you have non-trivial, proper non-trivial normal subgroups. So it means that you can be simple. So a finely generated linear group, an infinite finely generated linear group, is never simple. And this means that if you want to search for simple groups, you have to look at non-linear things. It's a non-linearity phenomenon. Right, so this is why these groups, I present them as groups acting on something, because they are given as automorphisms of certain structures, but they are not linear groups. Okay, so I will focus on measure equivalence now. We say that two countable groups, gamma and lambda, are measure equivalent if there exist two commuting actions of gamma and lambda that are measure preserving, free, and with a finite measure fundamental domain on some standard infinite measure space omega n. So this is, if you want, the measure theoretic counterpart of quasi-isometry. Because you can characterize quasi-isometry in a similar way by changing measure preserving by continuous. You change finite measure fundamental domain by compact space, compact metric space. Compact fundamental domain on some metric space XD. Okay, so what is our goal? Our goal is to do the same thing as Capra-Remy or as Skipper, Witzel, and Zaremski. We want to produce an infinite family of finitely simple groups that lie in different equivalence classes. So here I want to do measure equivalence. So we want groups that are pairwise non-measure equivalent. Okay, so naturally we won't do this by just manipulating measure equivalence itself. We will manipulate an invariant. So what is the invariant we are going to work with? We are going to work with L2 numbers of discrete groups up to proportionality. So this is invariant by measure equivalence. So now the goal is to produce groups that have non-proportional sequences of L2 numbers. We had 3 families before. So, well, we can pick a candidate among these 3 families. And I will pick Kac-Moody groups over finite fields because it's a huge family. And we can expect that since the family is really big, we can expect that people have non-proportional sequences of L2 numbers. The main tool we're going to use about them is that they are lattices in a product of their completions. So this, it's because a discrete group in general has not too much structure. So we are going to view them as lattices lying in some bigger thing, in some topological group. And we're going to use the structure of the topological group to study the L2 numbers. So this is given by this theorem. So this theorem, due to Peterson, tells that if we have a lattice in, for instance, a totally disconnected group, so here totally disconnected will be enough. I think this is true in a more general setting. Then the sequences of L2 numbers of lambda and of k and of g are proportional. So we can really work with the topological group. Now, for this topological group, so these are the completions of these Kac-Moody groups, we have a formula for L2 numbers. Well, this formula is quite general, but it is still hard to manipulate. In concrete examples, if you really want to do computations, you will have to do some combinatorics, some algebraic topology on Coxeter groups. Okay, so in this first talk, I would like to present mainly this third item. So I would like to present Kac-Moody groups or finite fields. So in order to do this, I would like to present these groups as groups that act on certain geometries that we call buildings. So most of the talk of this first talk will be about buildings. Okay, so let me begin. So Coxeter systems will be important all along the 2 talks. So I will give a definition from the very beginning. A Coxeter system is the data of a finite set S and a group given by generators of relations. So it's W. It's generated by the set S, and the relations between the generators are given by these coefficients MST. So we ask that MSS is equal to 1. This means that the MS of S are involutions, and then we ask that the MSTs are bigger or equal than 2 when S is different from T, or equal to infinity. So equal to infinity means just that we do not put any relation between S and T. The matrix that contains these coefficients is what we call the Coxeter matrix of the Coxeter system. Now, we say that the Coxeter system WS is irreducible if we can write it as a product of 2 Coxeter systems. So by product of 2 Coxeter systems, I mean the following. So a Coxeter system is given by its generators and the relations between these generators. So the direct product between 2 systems is just you ask that all of the generators of one group commute with all of the generators of the second group. Or if you want, the MST is equal to 2 whenever S lies in the first group and T lies in the second group. and we are irreducible if we cannot do this, if we cannot write it in this way. Okay, among Coxeter groups, we have affine Coxeter groups, which can be characterized, for instance, as Coxeter groups acting as a reflection group on the Euclidean space. So, well, this is more precisely. They act properly, compactly, the fundamental domain is simplex. But, well, they behave nicely as reflection groups on the Euclidean space. This is not really important for us. What is important is that we have a complete list of these groups. So basically, these groups will be classified in terms of some diagrams. I will come back later to these diagrams. And the thing is, we have a list for these diagrams, so we can say exactly when someone is not affine, when someone is affine, or when someone is not affine. Okay, now I want to generalize the previous situation of affine Coxeter groups. So affine Coxeter groups, they acted nicely, they behave nicely when acting on the Euclidean space. So now I want to define a space on which W will naturally act as reflections, also in a nice way. So this is a little bit technical. I need to define something we call a type. So the type is given as follows. So we take a delta to be a cardinal of S-1 dimensional simplex. And we identify each phase of codimension 1 to a generator in S. So this, we can do it because we have exactly cardinal of S phases of codimension 1. So we can label each of these phases of codimension 1 by generator in S. And then when we take intersections of phases of codimension 1, we can identify any phase of delta to a subset of S. And the bigger the codimension, the bigger the subset of S. Now we define, so well, it's a little bit abstract definition. So we define the Coxeter complex of WS as the space sigma given by, so it's the product of W with this simplex delta quotient by some relations. So let me explain this. You have the following. It's, you take a copy of delta for each element of W, so you have many copies of delta, and now basically this equivalence relation corresponds to gluing these simplices, and we glue them. In a certain sense, we are following the Cayley graph of the group W. If you want, this is done in such a way that the resulting space sigma is dual to the Cayley graph. So this is why I say we are going following the Cayley graph. But, well, let me give you some examples. I think it's better. So if we are given the group given by 3 generators of order 2, because we want it to be a Coxeter group, where the products of these generators have order 3, then I claim that the Coxeter complex associated to this will be the Euclidean plane. It is a Euclidean plane that is tiled by equilateral triangles. So how do we see this? How can we geometrically see what is the Coxeter group? I claim that the Coxeter group is the following. You choose a triangle. You can choose this one, for instance. And basically, the Coxeter group W will be the group generated by the reflections on this straight line, on this straight line, and on this one. So basically, it will be the reflections with respect to the 3 lines that contain the edges of a given triangle. And in here you can see the construction if you want. Like basically the simplex, we took the standard cardinal of S-1 dimensional simplex is just a triangle. And what we did is basically we took a copy of this triangle for each element of W, and then we had glued them. We glue these triangles following the edges in a certain way, and I think that the dual The dual graph of this will be the Cayley graph of the group W with respect to the generating set S, that here it is RST. We can play with the coefficients, so we can take again 3 generators, but instead of choosing 3, 3, 3, we can choose 2, 4, 6, for instance. And if we choose 2, 4, 6 by a theorem of Poincaré, I claim that we do not obtain. We can geometrically see this as reflections acting on the hyperbolic plane. Right, so this is an example of a non-affine Coxeter group, and we can see geometrically that it is not affine because, well, we can see it combinatorically because this is not. I claim that this does not appear in the list of affine Coxeter groups, but we can also see it geometrically because the Coxeter complex is not naturally given as the Euclidean space tiled by something. Okay, so if you want, the picture of a Coxeter complex is this. The picture is you take it's like a tiling of a certain space, and now a building is a simplicial complex that is obtained by gluing these tilings. So and again, we have to glue enough tilings. We glue them a lot. So more precisely, this means a building is a simplicial complex X with subcomplexes called apartments, which are isomorphic to the Coxeter complex of a given Coxeter system with 2 conditions. So the first one is that any 2 simplices of X lie in a common apartment. This means that basically we have glued enough Coxeter complexes so that we can view any 2 simplices inside of a tiling always. And we also have a compatibility condition. So this is useful when we want to define something we call a Coxeter value distance. And this compatibility condition means that if we have 2 simplices somewhere in the building, and we have 2 apartments that contain them, we know that there is at least one that contains these 2 simplices. But if we take 2 apartments that contain them, there is an automorphism that carries one into the other, fixing these 2 points. So it means basically that the position of these 2 simplices, A and B, is like independent of the apartment that passes through them. Now some vocabulary. The group W is what we call the Bible of the building, and the number of top dimensional simplices containing a given face of codimension 1 is what we call the thickness of that face. So let me give you an example of this. A homogeneous tree here in the left. So this is a building of dimension 1. Here the apartments are straight lines, so straight lines are geodesics if you want, and they are tiled by segments. And the tiling by segments is basically it's basically the action of the infinite dihedral group. So the infinite dihedral group, you can see it on the straight line as acting on 2 reflections with respect to 2 different points. So it's like you take the reflection with respect to 0, so it's x maps to minus x, and the reflection with respect to 1 in the same way. And this will generate an infinite dihedral group that will tile in this way. It will tile a straight line. Right, so the value group is this infinite dihedral group, and the thickness. So the thickness is the number is, well, thickness depends on a node here, and it is the number of edges that contain this node. So you can see that here the thickness is constant and it is always equal to 3. In fact, we could have chosen a tree that is a little bit different. We could have chosen 4 here and here 3, but here it is always 3. The right picture is, I would say, the local picture of an affine dimension 2. So here you see just 3 apartments that are Euclidean spaces, Euclidean planes that intersect each other. But I want to say this is just a local picture. It's just to say that the combinatorics of these objects becomes really complex when the dimension is higher. And you can see this, that, well, in practice, you have much more apartments that go in every direction. So this is just to emphasize that the fact that geometrically this becomes really complicated in higher dimension. And that really the only nice drawing we can make is the tree. Okay, so I presented buildings just to then talk about my candidate of finite present simple group, which will be Kac-Moody groups. So what is a Kac-Moody group? Well, it's a little bit abstract, but well, this he does an abstract construction in which he's given something we call a generalized Cartan matrix. And we have this generalized Cartan matrix. We can associate to each field a group. Now we don't want to work with generalized Cartan matrices. I just want to work with Coxeter matrices. So I say it in this way: when the coefficients of the Coxeter matrix of WS lie in 2, 3, 4, 6, or infinity, we can associate to this Coxeter group, we can associate a general Cartan matrix. And now this tells us that we have a functor that associates a field to a group. So this is just to erase the dependence on the general Cartan matrix. I just want to work with Coxeter groups. Now the group we obtain is what we call discrete Kac-Moody group associated to W and K. So it's a discrete Kac-Moody group because in fact we could have chosen others. But the choice is not canonical, but this is not a problem. Okay, so I will focus on the case where the field I choose here is always a finite field. So when we have a finite field, we have the following properties. First, lambda acts strongly transitively. I will not explain what strongly transitively is, but it means transitively enough in a certain sense. On two isomorphic buildings, x minus and x plus, that have constant thickness equal to q plus 1, and Weil group WS. So we have done this. We started with a Coxeter group, and we ended with the same Coxeter group as a Weil group on the building. Now, since lambda acts on these buildings, we can view it as automorphisms of these two buildings, x plus and x minus, and this group has a topology. We can view it with the compact open topology. So the automorphism of x plus and x minus are a topological group. And now lambda is a subgroup set of it, but it's almost never closed. So we take the completion. We take the G plus or G minus, the completion of lambda in respectively the automorphisms of x plus or the automorphisms of x minus. And I claim that in this case, if this Q is large enough, then the group lambda is a lattice in G minus times G plus. So it's an irreducible lattice in the product of these two completions. Now, the two results that are interesting for us are the following. First, due to Capra-Rami, if W is non-affine, so this is why being non-affine and characterizing non-affine Coxeter groups is important. If W is non-affine, irreducible, and Q is large enough, the group lambda is simple. And second, due to Aronnaco-Muller, if Q is large enough and the entries of the Coxeter matrix of W are finite, then the group lambda is finitely present. So if we take all of these hypotheses together, we choose a non-affine Coxeter group, irreducible, with finite entries in the Coxeter matrix, and we choose Q to be large enough, we have a finitely present simple group that is a lattice in a product of topological groups. And I will end here for now. We will continue this in the second talk. So I will talk about cohomology and really how to relate how to compute eligibility numbers for these groups, for the completions of these Kac-Moody groups. Thank you very much.